In this lesson, we're going to talk about more differentiation rules. In the previous lesson, we talked about some basic rules that you can use to take the derivative without having to use the limit definition all the time. So now we're going to talk about some rules that we can use for more complicated functions. So we're going to start with the product rule. If we have a function u of x and we have a function p of x, and they're both differentiable, then we can say that the derivative of u times v is the derivative of u times the function v of x plus the function u of x times the derivative of v of x. Now we can also look at this with prime notation here. When we take the derivative of u times v, we would take u prime times v plus u times v prime. Now down here it's stating the rule in words. You take the derivative of the first factor times the second factor plus the first factor times the derivative of the second factor. Let's look at our first example. So we have a function f of x, and it's defined by two factors. We have 5x squared plus 4, and we have x to the third plus 11. So we're going to look at this here, this first factor, and think about it as a whole new function. We're going to call that u of x. And then we're going to look at this factor as a whole different function. We'll call that v. So f of x is u times v. So now that we have it set up like this and we've identified what our u and our v functions are, we can use the product rule. So I take the derivative of u. The derivative of u is going to be just 10x. You bring the 2 down in front, that gives me a 10, and I have x to the first, and then the derivative of a constant is 0. So I get 10x here, and then I multiply that by v. So that's going to be multiplied by x to the third plus 11. And then we add the next term, which is going to be when you take the first factor, which is our u of x, 5x squared plus 4, and multiply it by the derivative of the second factor, which is x to the third plus 11. When I take the derivative of x to the third plus 11, I bring the 3 down in front. So I have 3 times x, and then this becomes a squared, and then the constant drops out. Now when I distribute the 10x and distribute the 3x squared, I get this here, and then I can combine like terms, so I can say that the derivative of f is 25x to the fourth plus 12x squared plus 110x. Now there's a couple things that I want to point out. Even though we used the product rule in the previous slide, we can still use the methods that we used in the previous lesson with the power rule. If I took the time to multiply that out first, I would have an expanded polynomial, and then I could just directly use the power rule. So a lot of times when you take derivatives, there's usually more than one way to do it. So here's an example of where we might have a function that we don't want to multiply out. It gets complicated because of this negative 2/3, because of the fact that this is raised to the 7th power. I don't know of anybody that wants to multiply that 7 times. So in this case, the product rule would be better, less messy. So a second thing that I want to point out, in the previous lesson when we discussed how we could take a function that was created by adding or subtracting two other functions or more together, we could take the derivative of the parts separately, and it would give us the same thing as the derivative of the whole function. That does not work with the product rule. If I take the derivative of 5x squared plus 4, we get 10x. If I take the derivative of x to the third plus 11, I get 3x squared. When I multiply that, I'm not getting the same thing as I did when I used the product rule. So these are not the same. So just be aware of that. Looking at example 2, we have the function g of x is equal to t squared minus 4 times t squared plus 1. Now, I could multiply that out first and then use the power rule to take the derivative of each of the terms. But since we're talking about the product rule in this lesson, we're going to practice with the product rule. So in part A, we're going to find the values of t for which g of t is 0. And then we're going to find the values of t which g prime of t is 0. And we're going to talk about the difference between these two. So to find where g of t is equal to 0, I'm just setting our function equal to 0 and I'm solving. When we solve, I can just factor this t squared minus 4 into t plus 2, t minus 2. The t squared plus 1 cannot factor over the real numbers, so I just leave that as it is. So the solutions that I get that are real are going to be -2 and +2. This doesn't have a real solution, so we're not going to see that show up in the real plane. So the function g of t is equal to 0 when t is equal to -2 and t is equal to 2. This is our x-intercepts. So these are our x-axis intercepts. Right now, t is acting as our x because that's the independent variable. So this is going to be where the function crosses the x-axis because that's where the value of the function is 0. Now, to find the answer to part B, we have to take the derivative and then set it equal to 0. So when we take the derivative using the product rule, I'm going to take the derivative of this first factor, which is 2t, times t squared plus 1. Then I'm going to add the derivative of the second factor, which is 2t, and multiply it by the first. When we multiply that out and combine it together, we get 4t cubed minus 6t. So now if we want to find the values of t when the derivative is equal to 0, we have to take that derivative and set it equal to 0 and solve for t. So this can be factored. I can pull out a 2t from both terms, and then I set each factor equal to 0. So I have 2t is equal to 0, so t is 0. And then I set this factor equal to 0, the 2t squared minus 3. And when I do that, I get t squared is equal to 3/2 because I want to add 3 and then divide by 2. And then when I take the square root, I get plus or minus the square root of 6 over 2. Let's look at what this means. In the first part, we got t is equal to 2 and t is equal to -2 when we set the function equal to 0. Now, for these here, the values that we got when we set the derivative equal to 0, those are going to be where we have our local mins and maxes because that's going to be where the tangent line has a slope of 0. So that's going to be here. That's going to be negative square root of 6 over 2. And this point right here is going to be positive square root of 6 over 2. And then at 0, so this also will have a horizontal line for a tangent line. So now we're going to talk about the quotient rule. If I have a function that's defined as a quotient and I have a function u on top and v on the bottom, then to find the derivative of this, you're going to take v times the derivative of u minus u times the derivative of v, and then you're going to put that all over vx squared. So this is just the author of the book showing you different ways to look at it, different notations. Now let's look at example 3. We have a function here that's defined by a polynomial in the numerator and a polynomial in the denominator. We're going to call the top v and the bottom u, and we're going to use the quotient rule for this. So to find the derivative of this function, you're going to take v of x and multiply by the derivative of u of x, that's the top, and then subtract and multiply the top times the derivative of the bottom, and that's going to give me, and then you put that all over v squared. So now if I take the derivative of the bottom, so now if I take the derivative of the top, which gives me 3x squared plus 2, and multiply it by the bottom, and then I subtract the top times the derivative of the bottom, and then I divide that all by the bottom squared. So that's x squared minus 1 all squared. Then we're going to distribute and clean this up. What we end up getting is x to the fourth minus 5x squared plus 2x minus 2, and then all over x squared minus 1 quantity squared. So this is the derivative, and now if we want to evaluate it at x equals 2, we just have to plug in that value 2 and use our order of operations to find the value. So the slope of the tangent line at x equals 2 is negative 2/9. So let's go back for a moment to the beginning of the question. I want to show you something else. We have this function here where we have a polynomial in the numerator and in the denominator. I can rewrite this in a different way, and I could also use the product rule here. I don't have to use the quotient rule. If I rewrite this x squared minus 1 and raise it to the negative 1 power, I'm flipping that up and I'm writing it as an exponent with negative 1. So now I have it in a form that I could also use the product rule. You will still get the same answer, you're just going to be getting it in a different way. So let's look at number 5. The publisher of a musician's recently released autobiography expects that over the first 13 months after its release, the monthly profit can be approximated using this model. So T would be the months, so you'd plug in the month, and then you would get out the profit for that month. Oh, that has it down here, where P is in thousands of dollars and T is the months from the time of release. So part A says derive a model that gives the marginal profit of the book. So remember, marginal profit, we can estimate that using the derivative. Then part B says specify and interpret the expected marginal profit 5 months after release. And then specify and interpret the expected marginal profit 10 months after release. And then part D says, offer a mathematical argument to demonstrate that from 1 month after release, the monthly profit realized from the sales of the book decreased steadily. So now to find the marginal profit, we take the derivative. So I'm going to take the bottom times the derivative of the top, and then subtract the top function times the derivative of the bottom. And then that's all going to be over the bottom function squared. When we distribute and clean that up, we're going to get negative 100 times t squared plus 11t minus 5 all over t squared plus 5, all that squared. Now, if we want to evaluate this at t equals 5, we're just going to plug in 5 and see what we get. So I would put 5 in here where this t squared is, 5 in here, and I would get approximately negative 8.3. Now, because this is t is equal to 5, that represents 5 months after the book was released. Because this is a negative, that tells me the profit of the 5th month is on an interval that is decreasing. And then in addition to that, we know this is in thousands, so we can say that the publisher can expect a profit on the sale of the book to decrease by $8,300 from month 5 to month 6. Do the same thing at 10. If I evaluate the derivative at 10, I get negative 1.9. Remember, this is in thousands. Because this is negative and we know that it's in the thousands, we can say that we are approximating that the profit is going to decrease about $1,900 from month 10 to month 11. Now for part D, we were asked to show mathematically why we think that there's going to be a decrease in profit after the first month. If you graph that function and you looked at it after month 1, you would see that going from left to right, it is going down. It's a decrease. So here's our function. I graphed it on GeoGebra so we can take a look at it. First thing I want to do is I want to show you how you can find the local min and max on here. I want to stress that everything that I show you on here, you should be able to do by hand as well for the test. This is just a nice way to have a tool to check your answers and to graph your functions nicely. So if we want to find the local maxes and mins, you can click on Tools here. And then if we click on this, the extremum, and then it says down here, select a function. So I'm going to click on that function. And then it's going to show me where the local maxes and mins are. And then I can go back to the function by hitting the algebra button. If we look at this point right here, it says that maximum point here is at the point x is 0.4372, we'll round it, and then at over 100. That's this right here. Remember, the question was asking us to show that after the first month, it's all decreasing as far as the profit's concerned. There's a local max at x is equal to 0.437. And then so month 1 after that, this is the max. Everything after that 0.437 is going to be decreasing, which includes month 1. Let's find the derivative. I'm going to put in n derivative and click on this one and choose function. I'm going to put in f. I'm going to hit enter. Let me take out the first function. Let me block off these points here too. Okay, here's the graph of the derivative of f. Remember, the derivative represents the slope of the tangent line at any point on the function. When the slope of the tangent line is negative, that means you're on a decreasing interval. If we look to see where the derivative is negative, which gives us where all the places that we would have negative slopes on the original function, that would be from here over. All of these values lie below the x-axis. And we can continue to zoom in. The x-axis is a horizontal asymptote. But you can see from this point and on, everything is below the x-axis. So that means from this point on the original function, all the slopes of the tangent lines are negative, which means the function is going to be decreasing on that interval. So from 0.437, the function is going to be decreasing. Looking at example 6, we have a function that's defined by a polynomial on top divided by another polynomial on the bottom. And the question is asking us to find the equation of the tangent line at x equals 4. So we're not given the information for the corresponding y value that goes with x is equal to 4. So let's do that first. When you look at x equals 4 on this function, we need to know what that corresponding value of y is. So in the function, everywhere I see x, I'm going to plug in 4, and we're going to get that the corresponding value of y is 3. So the point where we're trying to find the tangent line on this graph is 4, 3. Now we need to find the slope of the tangent line, which we can do by finding the derivative. Because this is a quotient, we're going to use the quotient rule. So we're going to take the derivative of the top times the bottom, and then subtract the derivative of the bottom times the top, and put that all over the bottom squared. When I take the derivative of 2x5, we get 2. When we take the derivative of x minus 3, we get 1. So then once we distribute and clean up the top, we get negative 1 over x minus 3 squared. So this is our derivative, which gives us the slope of the tangent line at any point on this function here. So now if we want to find the slope of the tangent line specifically at x equals 4, we're going to plug in 4, and we're going to get the slope is equal to negative 1. And don't forget that we're plugging it into the derivative. Sometimes people forget and plug it back into the function. So now we know that this is the slope of the tangent line at x equals 4. So now we're going to put it in point slope form. We have our m, which is negative 1. That's we're going to put it here. And then we found our corresponding y value that goes with x equals 4. So since we know that that's on the function and on the tangent line, we're going to put in 4 for our x value and 3 for the y. And then to put it in slope-intercept form, we would distribute that -1 and then add 3 to both sides. So this is telling me that the tangent line at x equals 4 on that function is -x plus 7. This is telling me that that tangent line is going to cross the y-axis at 7, and it's going to have a slope of -1. Looking at our last example, it says the campaign committee for a politician estimates that in an upcoming national election, the politician can, by campaigning for X days in a particular county, secure 2.3x in thousands of votes. However, the campaigning cost of the money in the committee estimates that the cost for the campaigning of X days will be 7.1 x squared plus $210. So they set up this function as a ratio between the number of votes and the cost for those votes, where x is the number of days of campaigning. So we want to find f prime of 4 and f prime of 6. So using the quotient rule, 2.3x is going to be our u, and 7.1 x squared plus 210 is going to be our v. So when we use the quotient rule, we're going to take the derivative of the top, which is 2.3, times the function on the bottom, minus the derivative of the bottom times the top, all over the bottom function squared. Now, when we simplify that, we're going to go through and we're going to get that the derivative is -16.33x squared plus 483 over 7.1x squared plus 210 all squared. So now that we have the derivative, let's evaluate it at 4 and 6. When we plug in 4 into our derivative, we get approximately 0.0021. And when we plug in 6, we get approximately 0.0005. Now remember, that was in thousands, so we've got to move the decimal place over 3 places when we interpret this. So this politician is trying to figure out the best number of days to campaign. And so this first example here, when we plug in 4, that tells us if he campaigns for 5 days instead of 4, he'll get about 2.1 more votes for every dollar he spends. But if he campaigns for 7 days instead of 6, he'll lose about half a vote for every dollar. That's this one right here when we plugged in 6. Here's the interpretation we just discussed. And then here are some questions that you can use for practice when you're done with your homework. I would definitely suggest trying to answer these questions.